Welcome, B-Tech beginners. Okay, if you're staring at your computer network syllabus right now and feeling, well, a little overwhelmed, just take a deep breath. I am here as your digital study buddy, and today we're knocking out a massive concept from Module 1. This explainer is all about the physical layer. Specifically, we are tackling topic 1.11, multiplexing techniques. By the end of this, you're going to understand exactly how data actually travels across networks, and you'll be able to confidently check this whole topic right off your roadmap.
Okay, let's dive right into this. Have you ever actually stopped to think about the sheer volume of data flying around the world at this exact second? Think about your own neighborhood for a minute. You've got dozens of houses, right? They're all streaming 4K movies, downloading massive game updates, jumping on video calls, literally, all at the exact same time. Yet all of that data is somehow traveling through just a single, shared, main cable buried under your street, and it doesn't turn into a jumbled mess. How on earth is that physically possible?
Well, to understand the solution, we first have to understand the core problem, the single cable problem. In networking, a cable, or even a wireless channel, is just called a medium. Now, if your computer and your neighbor's computer both try to send electrical signals down that exact same medium at the exact same millisecond, those signals will literally crash into each other. The voltages mix together, the data totally corrupts, and the result? Total digital garbage. It's kind of like two people shouting into the same walkie-talkie at the exact same time. Nobody hears anything but static and noise. So we needed a foolproof way to prevent these collisions.
And that is where our engineering solution comes in: multiplexing. You can think of multiplexing as basically the ultimate master of sharing. It's a clever technique used down at the physical layer to combine multiple, distinct data streams into one single, unified signal that can easily be transmitted over a shared medium. And once it reaches the other side, a device called a demultiplexer steps in and separates them all back out. It is honestly pure networking magic. And there are three main ways engineers actually pull this off.
All right, the first technique on your syllabus is FDM, which stands for Frequency Division Multiplexing.
As the name suggests, this method takes the total available bandwidth of a channel and slices it up into different frequency bands. And this brilliantly illustrates how FDM works in the real world. Just think of an old-school car radio. When you turn it on, all the stations in your city are blasting their audio through the air, which is the exact same medium at the exact same time. But they don't overlap, right? Why? Because, say, the pop station is transmitting at exactly 98.1 megahertz, the rock station is hanging out at 100.5, and the jazz station is at 107.7. FDM creates these invisible, dedicated lanes of frequency for each data stream. They're all traveling together, but because they're vibrating at totally different frequencies, they completely ignore each other.
Moving right along our syllabus, the second major technique is TDM, or Time Division Multiplexing.
So while FDM divides by frequency, TDM takes a totally different approach. Imagine you're in a highly organized study group meeting. If everybody talks at once, it's just chaos. So you set a strict rule. Each person gets exactly 1 second to speak, going right around the table in a circle. Person A speaks, then person B, then person C, and then boom, right back to person A. That is exactly what TDM does with data. It gives each user a tiny, dedicated time slot to transmit their digital bits. The multiplexer switches between the users so incredibly fast, we're talking thousands or even millions of times per second, that to the actual users, it feels like they have a continuous, dedicated connection, even though in reality, they're actually just taking turns really, really quickly.
So the crucial point is really understanding the contrast between these two. If you get a question on your exam asking to compare them, and you probably will, remember this core difference. FDM divides the physical space of the channel into separate frequency lanes. It's kind of like painting multiple lanes on a highway so cars can drive side by side. TDM, on the other hand, uses the whole highway, but only lets one car on it at a time, just in blindingly fast alternating turns. Simply put, FDM relies on frequency separation, while TDM relies on time synchronization.
And that brings us to our third and final technique for topic 1.11, WDM, or Wavelength Division Multiplexing.
Now, if FDM and TDM are the classics, WDM is absolutely the modern superpower. It's specifically designed for fiber optic cables, where we transmit data using light instead of electricity. To wrap your head around this one, picture a simple glass prism. When you shine a white flashlight into a prism, it splits out into this beautiful rainbow: red, orange, yellow, green, blue. Well, WDM does this, but in reverse. We can take one data stream and turn it into a red laser beam. Then we take another data stream, turn it into a blue laser beam, and another into green. Because different colors of light naturally have different wavelengths, we can shoot all of these colored lasers down the exact same glass tube at the exact same time.
The colors just pass right through each other without interfering at all.
Which leads us to this seriously incredible number. One single fiber optic cable, which is often no thicker than a single human hair, mind you, can carry terabits of data per second using WDM. This is the exact technology used in those massive undersea cables that literally connect our continents and form the backbone of the entire global internet. It's also how 4G and 5G cellular networks eventually route their massive data loads. By stacking dozens of different wavelengths of light into just one medium, engineers have achieved these mind-boggling speeds that make all our modern streaming and gaming possible.
Let's move to a quick recap and see how this builds our foundation. Here is your quick cheat sheet, so you can confidently check Topic 1.11 off your computer network's roadmap. Multiplexing is, at its core, simply the master of sharing a single medium. We covered FDM, which shares by dividing the channel into distinct frequency bands, kind of like radio stations. Then we explored TDM, which shares by time, slicing the channel into high-speed time slots like polite speakers in a meeting room. And finally, WDM, which shares by wavelength, using different colors of light to push massive amounts of data through fiber optics. You've now got a really solid grasp of how the physical layer handles all this traffic.
But I want to leave you with this final provocative thought. Right now, we're literally splitting time, frequency, and light just to keep up with the world's insatiable appetite for data. But think about it. With AI, virtual reality, and billions of new smart devices coming online in the next decade, eventually, even WDM is going to hit its physical limit. So for all you future network engineers out there, as our data needs outgrow the systems we just learned about today, what new multiplexing superpower will you invent next? Think about it. Thanks so much for joining me on this explainer, and I will see you in the next module.